Okay, so in this video, we're going to talk about how to create an interval estimate for a population mean when we know the standard deviation of the population. So you might be wondering, when will we know the standard deviation of the population? Well, typically we don't. Most of the time we don't. And if you're not sure whether you know it or not, be safe, be conservative, and assume that you don't know it and you can estimate it from your sample. But there are situations, there are times when we do know the standard deviation of the population. For example, we have a lot of historical data that gives us a good representation of the population. Sometimes we can use that data as a value for the standard deviation of the population, right? We can calculate it from that data. Some stuff, for example, like IQ, has a mean of 100 and a standard deviation of 15. That's a known. Now, have we collected the IQ of every single person who's ever lived or who lives right now? No. But again, we have such a large amount of historical data that we basically take this as the population parameters. Quality control, again, that if you're, say for example, you're producing something, you're creating something, right, you probably have good control over the production, and you have a lot of, again, information to know what the population parameters are, especially the standard deviation. So this is important because if we know the mean and the standard deviation, then we can use this to create a sampling distribution. Remember, we learned about that in Chapter 7. Why do we care about sampling distributions? Remember, if we have it, we can calculate probabilities. So that's why it's important to know the mean and standard deviation, because if we know that information, we can create a sampling distribution. From that, we can calculate probabilities, which, if you haven't figured out yet, in statistics is very important. We want to know, hey, what are the chances that this will happen or this won't happen, right? It really helps us better understand our data and make informed decisions. So if 95%, for example, of all the possible sample means, right, so basically if we took our population, we randomly sampled from it, and we calculated a mean, and we did that over and over again, if 95% of those possible sample means fall within about 2 standard deviations of the mean, we can say that 95% of all the interval estimates that we create include the population mean. So that's important. So remember, in our previous video, we were talking about Hillary and Bernie, and we had those interval estimates, and then we said, hey, we're 95% confident that the true population parameter lies somewhere in that interval estimate. This is where it comes from, right? Understanding conceptually that we have this idea of a sampling distribution, and we create an interval estimate, and that we are so certain, 95% for example, that interval estimate truly includes the population mean. So let's kind of walk through an example. So we have a sample size 100. Here's the mean. The known standard deviation is 20. Remember, from this, right, this is for the population, right, of all of the people or entities, elements, whatever, right, this is the mean and the standard deviation. But remember, that population also has that point estimate, right, whatever we're interested in. So in this case, the mean, right, also, if from all of our samples of size 100, we can create a bunch of samples, all of them possibly, and put together a sampling distribution. Well, that sampling distribution has its own standard deviation, which, remember, from Chapter 7 is called the standard error. So the standard error, remember, is the standard deviation for the sampling distribution. It's calculated by taking the standard deviation of the known population and dividing it by the square root of n. So it's 20 divided by the square root of 100, right, it comes out to be 2. So 2 is the standard error for the sampling distribution. That is the standard deviation for the sampling distribution is 2. Okay, so let's look at this. This is our sampling distribution of x bar, our mean, which was 82. So let's assume that this is the true population parameter, 82. That's its mean. Its standard error, right, the standard deviation of the sampling distribution is 2. We just calculated that. So let's say that we're working with that 95% confidence. Let's just assume that's the number we want to choose. It's very common in statistics. We can say that 95% of all of the mean values would fall in this shaded region. So remember, 95% of all x bars, what does that mean, Kristen? Remember, if we took our population and we sampled 100, let's say that they're people, just it's easier to conceptualize, 100 people, and we calculated some type of average, right? And we did that over and over again. Every time we did that, we'd get a different get a different mean. And if we plotted them, it would look like this distribution, where 95% of those averages that we calculated would fall in the shaded region, which happens to be almost 2 standard deviations away from the mean. Well, how do you know that? How do you know it's about 2 standard deviations? Well, the exact number is 1.96, and we have seen this before. We have seen, is it this one? From chapter 6, the area under the curve for any normal distribution. Right here's about 95, it's 95.4, is 2 standard deviations, right? 2 standard deviations away from the mean. We've seen this, we've calculated this, where we know the area under the curve, right? We can use that to calculate the number of z-scores or the number of standard deviations data falls from a mean. So if you look over here in the Excel example, right, if we want to know exactly what that z-score is, right, what we can do is we can find out what this p-value is. So if we know that the area under that curve, right, was 0.95, right, 95%, then that means that there's 5% left for either of the tails. And because it's symmetric, we can take that 5% and divide by 2 to get 2.5%. So we know that there's 2.5% of the data up until this point here. So let me say that again. So if we know, we're trying to figure out what the z-score is basically, right? What is this value here? We know from this table, this figure, 95.4%, right, is 2 standard deviations. Right now we're working with 95%, not 95.4. So we want to figure out exactly what that z-score is. It's not 2, it's 1.96. It's very close. But how do you get that 1.96? We've already learned how to do this in previous chapters, but I'm just reviewing this, right? What we have to do is we have to find out what that p-value is, right? The probability, right? That area. What is this area up until this point? Because if we know that, then we can find that z-score. So, right, what we can do is we can subtract 95%, right, 0.95 from 1 to get 0.05, this value right here in A8, right? But remember, that's all the area under the curve that's not in that region that we were looking at, that shaded region. So it's 5%, but remember, because it's symmetric, the distribution, half of that is in this upper tail and half of it is in that lower tail. So if we take 0.05 and we divide it by 2, we get 0.025. So 2.5%. So then we can use our equals norm.s.inverse, right, function for that 2.5% to get this z-score 1.96. So basically what this figure shows is that 95.5% of the area under the curve falls within 2 standard deviations. If we want exactly 95% of the area under the curve, right, we have to use this little formula, which we've learned about before, to find out that it's actually 1.9 standard deviations of the mean. So if we go back to this figure here that we're looking at, Kristen, where did you get 95% and 1.96? Where's all this coming from? Right, we're just building off of what we've learned about in previous chapters, right? I've told you in the beginning of this chapter, 95% is very common, right? Why 95%? Because, you know, if you're thinking about, you know, how confident do you want to be? 50-50 is a wash. That's not confident. 70, 80, 95 is you're basically saying we're super confident. 90 is like, yeah, we are, but there's still a lot of error in there. There's still a lot of chance. 99 is really confident. So usually 95 is you're pretty confident, but there's still a little room for wiggle, if you will. So that's where the 95 came from. That's the area, again, under the curve that all of our means, right, would fall. So then if we want to know, well, how many standard deviations from the mean is 95%? Well, that's what we just calculated. That was the z-score. It's 1.96. So then we could take that 1.96 and then specifically for this population, in the sampling distribution, its standard deviation, its standard error is 2. Right, we can multiply those together, 2 times by 1.96, to find out that this range, this interval, goes from the mean, right, plus 3.92 and minus 3.92. So if we subtracted 3.92 or we added 3.92 to 82, which is our mean, we would get an interval that falls from about 78 to 85, 86. So basically, what I'm showing you is how to create that interval estimate and where these numbers come from. Basically, right, you have your point estimate, and then we say, okay, we want to be 95% confident, right? We want 95% of all those x values to fall within this region, right? That's 1.96 standard deviations away from the mean. Well, for this particular, because remember, every sampling distribution is going to be different based off of the population parameters, right? And this one, we happen to have a known standard deviation of 20, right? Every population is going to have a different known standard deviation. So for this one specifically, and for this sample size of 100, the standard deviation, right, the standard error for the sampling distribution is going to be 2. Right, so for this specific sampling distribution, for this specific population, right, using this sample size, right, 1.9 standard deviations, right, is going to be that 3.92 value. So basically this 3.92 is always going to be, different depending on the population that you're working with and the sample size. But it will be used to create this interval estimate. So basically what we've just calculated is actually the margin of error. So we've talked about this, let's talk about a related but slightly separate topic. Is what if every time we sampled, right, for 100 people, working with people, just to make it simple, every time we sampled 100 people and asked them about something, we created an average, right, x bar, we'd get a different mean every time, right? We'd get different point estimate values, right? So let's say the first time this was our point estimate. If we created our interval estimate, we notice that this interval actually includes the true population parameter, mu, right? We know this. So we see that this interval includes the true population parameter. Let's say that we took a different sample, right, x bar 2, when we calculated this mean, and we created the interval estimate. So again, it's that point estimate, whatever the average is for that sample, and we added our 3.92, which we calculated back in this slide. Whoops, right? It's just that 1.96 times by 2, right? For that interval, that also includes mu, the true population parameter, right? But for this one, x3, notice that our interval estimate does not include the true population parameter. So remember, by chance, sometimes you're going to get a sample statistic, point estimate, and you're going to create your interval estimate that does not include the true population parameter, which, remember, that is what we're actually interested in. So sometimes, by chance, our interval estimate is not going to actually include our population parameter. How often? Well, we've been working with 95%. So this figure is basically showing that if a point estimate value is outside of the 95% shaded region, right, the interval will not include the true population parameter. So this one you see right here, x3, it's outside of that shaded region. So therefore, it's not going to include the true population parameter. Therefore, we can say 95% of all the intervals formed will include the true population mean mu, right? This one does, but this one doesn't. It happens to fall outside of that shaded region, right? What is the area under that curve, right? We already calculated that, right? 95%. So there's 0.25 here, or excuse me, 2.5% here, 2.5% over here, which is 5% in total. So 5% of the time we're not going to get an interval that includes the true population parameter, but 95% of the time we do. So that's where we get the idea of that we can say with 95% confidence that the interval estimate does include the true population parameter. This is the build up to it. This is why we need to understand the data. We need to understand the true population. Do we know its standard deviation? If not, we'll have to calculate it. But from that, we can say what is our sample size. We can create the standard error, which is the standard deviation of the sampling distribution. And we can use the idea of the area under the curve, this 95%, to create, to find z-scores, which we can use to create, to find out what this 3.92 value is, to basically figure out are basically that interval estimate. So these are just some other definitions. You can look through these, right? Confidence level is 95%. That makes the confidence coefficient 0.95. Confidence interval, right, from this example that we just calculated, right, that ends up being our confidence or interval estimate, 78 to 85.92, whatever it is, right? And that's what we calculated in the Bernie Sanders and Hillary Clinton example, right? So we'd say that we are 95% confident that the true population parameter lies somewhere within that interval estimate. And then the other thing that we're just going to have to know is alpha. So what is the relationship between alpha and the confidence level? It's just 1 minus the confidence level. So if we're talking about 95%, so 1 minus 0.95 is 0.05 or 5%. So that's a relationship between alpha and confidence level. What is alpha? I don't understand this. When we go to calculate our z-scores, we need to know alpha. So for example, we worked with 95%. That's the confidence level, therefore alpha is 0.05. So remember, we had to divide alpha by 2, right, to get 0.025, which was the area right under the curve. So then when we go to calculate our z-scores, we're going to put in this value to get that z-score. So see how it's 1.96. So we'll show that in our next video. We're actually going to go through an example together to understand where does alpha come from, how do we create the interval estimate. So last thing I want to show you real quick is for our formula right here, we keep talking about this point estimate is equal to, or excuse me, our interval estimate is equal to our point estimate plus or minus the margin of error. This is the margin of error. This is what we calculated in this slide. It's equal to the standard error of the sampling distribution times by this z alpha divided by 2, right? And we saw that in this slide, right? Our margin of error is 3.92. What is it equal to? Our standard error 2 times by our z-score 1.96. So that's where that margin of error comes from. That's what it is.